All right, you guys. I'm going to go ahead and run through the Unit 8 circles review just to kind of help you out if you're struggling on any particular problems. So again, feel free to pause, rewind, fast forward. I'm going to try to go through this as quickly as I can because there's a lot of questions here. So here we go. The first part, it's starting out, I'm kind of going in reverse. So we're starting with the end of Unit 8 first. So these are just our equations for our circles. Please remember these formulas are on your formula chart. It's the very, very bottom of the page, right? So remember the equation of a circle. I'm just going to go ahead and write that really quick just as a refresher is x minus h squared plus y minus k squared equals the radius squared, where the h, k are the center of the circle, right? So clearly on number 1 here, the center of my circle is going to be 2, 0, because it's always the opposite of the number that's in the parentheses because we just want the number behind the minus sign. And there is nothing with the y, so that means we did not move in the vertical direction. So we just keep that at 0. And then, of course, the radius is going to be the square root of 6.25, which is going to give us 2.5. So with those two bits of information, we should be able to easily graph our center at 2, 0, and then our radius at 2.5. So I'm just going to go up 2.5 and right 2.5 and then down 2.5 and then left. All right, and then just draw the best circle you can with your boundary points. Well, I thought that was going to draw a nice circle for me. And then, let's see if that goes. That's a little bit better. Good enough. Doesn't have to be perfect. Okay. Moving on to this guy over here. So same exact thing. He's clearly in standard form. So the center on this one is going to be -3 and then +3 halves, or 1.5, right? If you want to go ahead and just write that as a decimal. And then the radius, of course, is going to be 2. That's all we have to do is pull out the center and the radius. So -3, +1.5. Right, so there's our center, and then we're going to go out 2 from there. 1, 2, 1, 2, 1, 2. And voila, there's our circle. Enough. All right, number 3, it says write the equation of the circle. Okay, well, we're just going backwards. So in order to write the equation, we need the center and the radius. If you're not given both of those pieces of information, then you'll be given enough information to find the center or the radius. So here we go. On this first one, we have the center, which is great, right? So here's our HK. But it just gives us a point on the circle. It doesn't give us the radius of the circle. So yeah, so we're going to need to figure out what the radius is, right? And so this one's a pretty easy one to find the radius of, because if you'll notice that the x's are both 0, right? So really, I'm not moving anywhere on the, everybody's on the y-axis, and I'm starting at 1/2, and I'm going up to 8. So just by understanding that little factoid, that means our radius is 7.5, right? Because all I'm doing, I'm not moving left or right at all, so I don't have to worry about the horizontal. I'm just starting at 1/2, and I'm going up to 8. So that's a radius of 7.5 from the center, okay? If you want to do the distance formula or whatever, you're more than welcome to, right? But we don't really have to do all that work when only the y values are changing and not the x values. All right, and then now we can just throw all those numbers into the standard form, which will just give us x squared, since again, we're not moving in the x direction, but we are moving up in the y direction by 1/2, so that's going to be y minus 1/2 squared. And then we want to take that 7.5 and square it, which is going to give us 56.25. Right, and that's it. That's our equation. All right, over here, we are clearly given the center as -5.3, 1, and the diameter Okay, well, obviously the diameter is not what we need. We need the radius, and we know the radius is half the diameter. So that's a nice, easy one to find. So now we can just put everything in. So it's going to be x plus 5.3 squared, because we're putting a negative behind a minus sign. So the double negative changes it to a plus sign. Plus y minus 1 squared. And then we need the 4.5 squared, which is 20.25. Right, voila. Number 5, they've given us the circle. So they want us to find our own information. So that's a pretty easy gig. So the center of this circle is clearly 4, 1. Again, make sure you're paying attention to the units. These are all going by ones. And the radius, let's see if we kick over. I am going to assume that's hitting that point perfectly. We wouldn't be able to ask you otherwise, right? So it's going from 4 to 9. So it looks like our radius is 5. And yeah, now that we have the information, once again, x minus 4 squared plus y minus 1 squared equals 25, the radius squared. Okay, all right, moving right along. All right, remember these are the equations in general form. So this is what we finished up our notes on yesterday, and this is where we need to complete the square. Right, so I do this in 3 little mini steps. So the first thing I do, and you don't have to do it just like me. If you just want to, I always like to put the little boxes. You don't have to put the boxes in. You can just go ahead and fill in the number once you know it. And then y squared minus 6y plus what? Right, so making another box. That's not a very good square. Let me try that again. There we go, better. Equals 12. So I haven't actually done any math. Right, all I've done is just put the boxes in and kind of set up my trinomials for my x's and my y's. And now I need to complete the square. Excuse me. So half of 4 squared is 4, so that's going to complete the square. Half of negative 6 is negative 3, and negative 3 squared is 9. So those are my 2 numbers that complete the square. And then don't forget, we have to keep that equation balanced at all times, right? The number 1 law of equation solving. So I know if I added some random 4 and 9 to the left-hand side, I need to make sure I add that 4 and 9 to the right-hand side and keep that equation balanced. Now, right now, this looks like a big, huge mess, right? But the whole point of doing this big, huge mess is we just completed the square so that we created these squared trinomials, which when we factor them are going to give us squared binomials. So if I factor x squared plus 4x plus 4, that's going to give me x plus 2 times x plus 2, which I can then write as x plus 2 squared. And then if I were to factor y squared minus 6y plus 9, I'm going to get y minus 3 times y minus 3, which gives me another squared binomial. And then, of course, over here, I end up getting 25. And voila. That's what I'm looking for right there, right? The equation of the circle going from general form to standard form. All right, may as well try that one more time. Here we go. Now this one's kind of all over the place, so that's why I really like my first step to be to get everything organized and in the right spot. So I want my x's first. So x squared minus 2x. All right, and then I put my little box for the completing the square portion of this. And then plus y squared plus 8y plus what? All right, and then that equals 19. Okay, so I didn't do any math. I just simply grouped everybody accordingly and then put boxes in just as my visual reminder that I'm completing the square here. So I need to fill in the boxes. So in order to fill in the box, you take half the b, which is negative 2. Half of that would give me negative 1, and negative 1 squared is positive 1. Then I want to take half of 8 over here, which is 4, and square it to complete the square. And then, of course, I can't forget that I need to add the 1 and the 16 also to the right-hand side and keep that equation balanced. And once we have that done, now we're kind of home free, right? Because now we're just going to factor these nice, pretty trinomials that we just created. If we factor x squared minus 2x plus 1, we're going to get x minus 1 times x minus 1. If we factor y squared plus 8y plus 16, we're going to get y plus 4 times y plus 4. So we can write that as a squared binomial. And then, of course, all that mess on the right-hand side is going to add up to 36. And voila, there's, oopsies, sorry about that. There's our equation in standard form, which is now going to make that nice and easy to graph if I needed to. Right? So obviously the center is 1, -4, and the radius is 6. Right? All right, the next one. They give me the center, which is amazing, but they don't give me the radius, and that's what I need to find, right? So there's two different ways you can do this. Me personally, I'm just going to do the distance formula because I know the radius is simply the distance from the center to any point on the circle. There's other ways you can do this, but I'm just going to go ahead and do it this way. So remember the distance formula is just x minus x squared plus y minus y squared, which is going to give me 3 squared, which is 9, and then 4 squared, which is 16, which is going to give me the square root of 25, which is 5. Right, so the radius is 5. Well, now that I know the radius, now I can write my equation, right? So use my HK center, x minus 1 squared plus y minus 2 squared equals, and then I need my r squared value, so 25. Voila. You can also, and I know some of you guys are probably doing this, you can also find your r squared value by simply, because this point is on the circle, if you want to, you can plug in that specific x and y into the x minus 1 squared plus y minus 2 squared, and you'll get 25, and it'll tell you that value that way, right? So there's always more than one way to do most of these math problems. All right. This next section, we're starting to get into all these lovely pictures, right, from our previous days of notes. Okay, so let's see. All this verbiage is giving me a lot of information, so my picture's probably going to get a little crazy here. So it says, assume that the lines that appear to be tangents are tangents. Okay. I don't really see anything that is a tangent line in this problem, so that's not really going to happen here. And then it says CQD is 120. Okay, CQD. Now that doesn't really look like a 120-degree angle, but that's okay. Arc BC is 30. Okay, so from there to there is 30. And, what does it say over here? BEC is 25. BEC, so that's this angle right here. All right. Now, things that I would definitely want to notice is that this angle right here is a central angle, right? And we know central angles are equal to their intercepted arcs. So I know this arc is 120. So I'm just going to go ahead and fill that in right now. The other thing I want to notice is that this angle is an outside angle, and he's half the difference of his intercepted arcs. So you know I'm going to be finding that. So I may as well just go ahead and do that right now. All right, so we're using the formula on our formula chart that tells us that this outside angle, 25, goodness, is half the difference of this arc AD. So I'm just going to go ahead and put that AD minus his closest arc, which is 30. Again, that's a formula on your formula chart. Outside angles are half the difference of their intercepted arcs. And then I can just solve that quick little equation. I'm going to go ahead and multiply both sides by 2 and turn that into a 50 so I can get rid of the parentheses over here. And then all I need to do is add the 30. So that means the measure of arc AD is 80 degrees. So this guy over here is 80. And I may as well keep going because I'm probably going to need a lot of these arcs. So I'm going to go ahead, even though I haven't even looked at the questions over here yet. I'm literally just solving this whole circle. And so really the only thing I have left to find is arc AB, and he's just the rest of the circumference, right? Because we have all the other arcs. So I just need to subtract. Let me grab my calculator because I don't feel like doing that in my head. I'm going to take 360. I'm going to subtract 30. I'm going to subtract 120. And I'm going to subtract that 80 we just found. And that gives me 130 degrees for this arc right here. Okay, so let's go see what we answered. Here we go. So number 9 is asking us for the measure of arc DC. Oh, we just did that already because his arc is equal to his central angle. So that's going to give us 120 degrees. All right, number 10 wants the measure of arc AD. Oh, we already found that because we used the outside angle formula there. So he's going to be 80 degrees. And then 11 asked for the measure of arc AB. Oh, we found him last because he was all the leftovers. So there's 130 degrees. And then the measure of angle ADC. Now this one is kind of tricky because you're like, ADC, I don't see angle ADC. That's because he's not drawn. So you are going to need to actually go in and draw angle ADC. And what kind of angle is that? Well, he's an inscribed angle, which means he is half of his intercepted arc. And his intercepted arc is the 130 plus the 30, which is 160. So he's going to be half of the 160, which is going to give us another 80-degree angle. So I know the angle wasn't drawn, but obviously you can throw a chord in there and draw your own angle. Okay, so that is that picture. All right, moving on to this picture. All right, lots going on. I'm going to label a lot of stuff here. Arc AE is 140. Okay, that doesn't look like 140, but alrighty, I'm going to just, again, trust the picture. It doesn't have to be drawn to scale. Sorry, turning the page, my paper copy. And then let's see, arc BD is Y. Okay. And arc AB is 2Y. Okay. And arc DE is also 2Y. Okay, cool. Please notice that all of these answers are going to look very incorrect because this is clearly much smaller than a 140-degree arc, but that's okay. Here we go. Let's see. I'll go in order this time. Find the measure of arc BD. Okay. Well, that's this guy right here. Well, so that means I'm basically solving for y. Well, that's going to be pretty easy to do because if you notice, we have an algebraic expression for every single arc that makes up the total circumference of this circle. So I know I can simply add up all the pieces. So 2y plus 2y, which is 5y, plus the 140. And I know all of that has to add up to 360 degrees. All right, so we can just solve that algebra equation. That's going to leave me with 220. So y is going to equal 44. All right, so that's going to give me the measure of arc BD, 44 degrees. Now I may as well go in while I just learned this lovely piece of information. I'm going to go in here in my picture. That's 44 degrees, which makes these two arcs 88 degrees. And of course, you shouldn't miss these questions, right? Because you can totally just add all that up again and make sure it adds up to 360. Okay. All right, let's go see what's next. The measure of arc AB. Oh, well, that's just this little minor arc, and we already plugged that y value in, so he's 88. All right, and the measure of arc DE. Okay, well, we just found that one too. He's also 88. Easy enough. And then the last one wants us to find the measure of angle BCD. So that's this guy right here. Well, once again, you have to ask yourself, is this angle inside the circle, on the circle, or outside the circle? And clearly this angle is outside the circle, meaning his vertex is outside the circle. So that means we're going to use the formula that so the measure, I'll just write this right here. The measure of angle BCD is half the difference of his intercepted arcs. And clearly his intercepted arcs are the 140 and that 44 that's closest to him. So 140 minus 44. Right, and that's going to give us half of 96, which is going to give us 48. And so that would be the measure of angle BCD. Again, that is totally on your formula chart. All right, next diagram. It's just a big cluster of diagrams here. Man, this one looks super complex. There's a lot going on there. Let's see, arc BC. Okay. So arc BC is 4x minus 50. Okay, so that's from here to here, 4x minus 50. Okay, arc DE is x plus 25. I'm just going to kind of put a little line right here. X plus 25. Okay, EF is x minus 15. And CD, goodness, CD is just x. Oof, okay. Oh, and there's more. And FB is 50. Oh, thank goodness. Okay, 50. All right. Oh, wow. Okay, so clearly the first thing we have to do is solve for x. And I'm hoping you notice that we are given an algebraic expression for every single arc that makes up this circle, just like on the previous problem. So we should definitely be able to add up all these arcs, and their measures have to add up to 360 degrees, right? So that is definitely going to be step number 1. So we've got 4x plus another x plus another x plus another x. So that's going to give us 7x, right? And then we have a positive 50 and a negative 50, which just cancel each other out, so I can kind of ignore those. And we have a negative 15 and a positive 25, which is going to give us plus 10. Right? And so that all has to equal 360. So we're going to solve that. We're going to subtract the 10. And looky there, we get 50. So now if you want to, I'm going to kind of go back in and like black or something underneath it. So we've got the 50. I'm going to kind of trace over him. And then if we plug in the 50 everywhere else. Oh, goodness. Sorry about that. If we plug in the 50 everywhere else, right? So this is going to give us, oh my gosh, sorry, my screen keeps moving on me. That's going to give us 35 degrees. And this is going to give us 75 degrees. And this one's going to be 50 degrees. And what is that going to be? 200 minus 50, so 150 degrees. And again, you can kind of check your math. That's 200, 250 plus 110, which is 360. So yay, that all makes perfect sense. Woof. All right. Now, according to all of these amazing questions, we are going to be solving for essentially every angle that we could possibly draw in this picture. So here we go. The measure of angle A. All right. Let's take this one step at a time. So angle A is clearly, again, an outside angle, which means he is half the difference of his intercepted arcs. Right, remember, the point of tangency is where one arc begins and the other one begins, or ends and begins. You know what I mean. So here we go. I'm just going to kind of do my math over here somewhere. So the measure of angle A is half the difference of his two intercepted arcs. Well, we already solved for x and plugged them all back in. So his furthest arc is 150 and his closest arc is 50. Right? So we're getting half of 100, which is 50. So the measure of angle A, I'm going to slide over here, is 50 degrees. All right, I'm going to kind of erase. This is why I love the iPad so much. I can make a huge mess and then erase it all and start over. All right, so our next one is the measure of angle BCA. Now, this is what I was just talking about a second ago. Do you see an angle BCA? No, but you can draw it. B to C to A. All right, so we're looking for this angle right here. Well, that is an inscribed angle, and he is going to be half of his intercepted arc. Right, so that's a nice easy one, right? He's going to be 25. All righty, let me erase that mess. Let's start fresh for the next one. How many colors can I make? All right, ABC. Okay, again, I don't see ABC drawn, so I'm going to do it myself. A to B to C. So we're looking for this angle. Well, that angle is also an angle on the circle, just like an inscribed angle. So he is also half of his intercepted arc. And we know what all those things are, right? That's 50 plus 35 plus 75 plus the little 50 at the bottom. So all of that is going to add up to 210. Right? Plus I know that also because I could just subtract 150 from 360. Right? But this whole arc right here is 210, and angle ABC is going to be half of that. So that's what gives us 105 for that angle. Remember, any angle whose vertex is on the circle is half of his intercepted arc. Because he only has one intercepted arc. It's not like the angles inside and outside that intercept two different arcs where we have to add or subtract. All right, next up, GBC. Oh my goodness, G. Okay, G to B to C. All right. Well, this is the exact linear pair of what we just found. He's on the circle, so he's going to be half of his intercepted arc, which is going to be half of the 150, so he's going to give us 75. And of course he's 75, because he's the linear pair to the ABC angle we literally just found. Right, so I'm just going to write that, linear pair. Right, those are the two angles forming that tangent. Okay. Again, more than one way to think about these questions. All right, let's hop to number 21. Angle FHE. All right, I got to zoom in a little bit. FHE. Let me get to a different color here really quick. I'm going to go with this green. FHE is this angle here, which would be congruent to his vertical angle here. Those are inside angles because the vertex is in the interior of the circle. And we know that they are the average of their two intercepted arcs that are being formed by those vertical angles. So the measure of angle FHE is going to be half the sum of 35 plus 50. So that's going to give us half of 85, which gives us 42.5. And again, that's on your formula chart. So 42.5 degrees. All right. Then, hold on, let me erase the mess so I can start fresh. There we go. I'll go with brown. Now what are we doing? CFD. C. Where's F? Oh, there we go. CF. I'm tracing it with my brown pen here. CFD. So we're talking about this angle right here. Well, that's just an inscribed angle. And we know he's going to be half of his intercepted arc, which is 50. That's the x we solved for at the very beginning. Right? So he is, of course, going to be 25 degrees. And voila, we just solved that crazy picture there. And all those angles. Okay. All right, moving right along. Number 23, it says the measure of angle A is 62. Okay, so I'm going to go ahead and put that in. The measure of arc BD is 120. So BD, the arc is 120 degrees. All right, now I don't know how much you remember. I don't like that this little thing is. I'm going to fix that. I don't know how much you remember, but these are all tangents, right? Tangent, tangents, tangents, right? And we learned that super awesome shortcut, right? It was in that yellow box in our note that said secret rule of tangents. It is so handy to know in problems that look like this, right? In case you don't remember, let me recap, right? The secret rule of tangents says that this angle and this arc will always be supplementary if the angle is being created by two tangents, right? And when I say that arc, I don't mean the whole, hold on, sorry. Right, I'm only talking about from here to here, right? So we're talking about this angle, right? And then his closest arc. They will always be supplementary. It only happens with tangents, not secants, not chords, anything else. It has to be two tangents on the outside of the circle. And that's exactly what's happening here. It's just a ton of tangents and their closest arcs. So I totally know, based on that information, that this angle has to be 60 because these have to be supplementary, right? I know that this arc right here has to be 118 degrees because these are going to be supplementary. And then in order to find the top, there's a couple of different ways you can do that. Number one, you can solve for the missing arc first because we just need to know what's left over from the 360 degrees. Or instead of using the circle, you could use the triangle. And we know the triangle sum theorem says those three angles have to add up to 180 degrees, right? And so we then know, sorry, I'm losing my voice. That we could just find angle E, right? So whether you use the circle or the triangle, that is totally up to you, right? I'm going to use the circle because why not? So I'm going to type that in my calculator. Again, that's pretty easy. So that's going to give me 122 degrees left over for arc FD, which of course means that this angle has to be 58 because, again, secret tangent rule, right? Now, I don't think it's going to ask me to find all of those things, but I've basically solved the whole picture, so why not? So here we go. We can just go over here and throw in some stuff. The measure of angle C, 60 degrees. The measure of arc DF, 122. And the measure of angle E, 58. All right, so again, secret rule of tangents. Please make sure you know what it makes problems like these so much easier. Right? There's other ways you can use your formulas to solve them, but it takes so much longer. Okay. All right. Oh my gosh, how many more of these diagrams? Oh my gosh, oh, so many. Okay, here we go. Plowing through. Let's see. Arc AB is X. Okay, I'm going to label that. And arc BC is 3X. Okay. Again, I'm going to go ahead and solve for basically everything in this circle because it's pretty quick and easy to do. It would be difficult to do if you did not completely recognize that this is a diameter. You have to see that. That is so imperative in this problem that you notice that AC is a diameter of this circle, right? So clearly, I know that this arc AC is 180 degrees. Well, if that's 180 degrees, then that means this inscribed angle is half of that, right? Because the semicircle is his intercepted arc. So he is a right triangle. Make that a little neater. Oh, kind of. Yikes. That did not turn out well. Okay. And I also know that this is another semicircle. So those two arcs have to add up to 180. So that means I can just do a quick 4x equals 180, which means x equals 45. So I know this arc is 45 degrees. And this guy is 3 times that, so he's going to be 135 degrees. Let me scooch this over a little bit. Sorry. So he's the rest of it. Okay, so at least we got all the arcs going on. Okay, so let's go see what questions they're asking us. So the first one says, what is the measure of arc ADC? Well, they're talking about this semicircle. So, of course, that's 180 degrees. Then on number 27, it wants to know the angle of our ABC. Well, we just talked about this, right? ABC is an inscribed angle intercepting a 180 degree semicircle, and inscribed angles are half of their intercepted arc. So he is, of course, the 90 degrees. All right, arc AB, well, we already found him, right, by solving for x and then just plugging that back in. So he's 45. Then we have the measure of angle A. That's one I haven't found yet in my picture, but that's pretty easy for us to find because he's an inscribed angle and he will be half of his intercepted arc, which is 135 degrees. So I just need to take half of 135, which is going to give me 67.5. Again, I'm kind of starting to feel like a broken record, like I'm literally saying the exact same things over and over and over again, right? These rules just keep repeating. Arc BC, all right, already found that, right? That's 135. And then the measure of angle C. Well, of course, angle C, another inscribed angle. So he's half of his intercepted arc, which is going to give us the 22.5 degrees. And I'll erase that. Okay, so again, notice I'm barely doing any math, right? The only math I did was this little tiny, this little tiny algebra equation over here. But if I didn't notice that I had a diameter and semicircles going on, then I'm not going to get very far in that problem, right? So make sure you're recognizing those diameters. All right, moving on. I think we're like halfway done. All right, here we go. Circle Q. The measure of angle ABC is 72. Now, that's going to be tricky because that's this whole angle. So I'm just going to kind of write that big right in the middle there. And arc CD is 46. All right. Well, that's not a ton to go on. But the first thing that I'm going to take care of before I do anything is I'm going to take care of this 72 because I don't like that fact that that 72 is split into two different angles. And I can actually figure out what those are, right? Because we clearly have, right, that 46 is being intercepted by angle CBD. So right away, I can cut that 46 in half and figure out that this is 23 of the degrees of that angle, right? And then I can just subtract the 23 from, what was it, 72? from the 72 and figure out that the rest of this is 49 degrees. So that's the first thing I'm going to do, is just know how the 72 is being split apart. All right. And I can't go without saying that it's very clear that I have a diameter, and I need to make sure that I pick up on that. Right? Because if that's a diameter, again, I can fill in all the rest of these arcs. I know every single other arc in this picture because this top half is a semicircle. So I know that all of that is going to add up to 180 degrees, which means this arc has to be 134 degrees, right? Then I also know that because I already found this 49 degree angle, he's intercepting this arc. So I know that that arc is going to be 98. Again, this picture is not very well to scale, but well, it's not bad. Right, and we know that the lower half of the circle is another semicircle underneath that diameter, right? So we can just subtract from 180 to figure out that this arc is 82. Okay, so that's a lot of really quick math that I can do. Again, all of that is coming from inscribed angles and diameters. Okay, all right, let's go see what we're looking for. Hopefully we found most of it already. The measure of arc CA. Okay, well that's a minor arc because it only used 2 letters. So we're just going to be adding the 46 and the 98 together. Which is what? Going to give us 144. All right, so hopping over here. Turn the page. So 144 degrees. All right, then we want the measure of arc BC. Well, I've already got that labeled in my picture. Yay me. So 134. Then we want AD, 98. Again, I've already done all this math. So I'm just start filling in answers. The measure of angles C. That one I haven't gotten yet. Let's come back to that one in just a second. Actually, no, let's not. Let's go ahead and take care of it. Angle C is kind of a tricky one at first when you look at it, because when it says angle C, we're talking about this angle right here clearly. Now the problem is he's technically an inscribed angle, but he doesn't go all the way through. And even if he did, I would have no idea what part of the 82 degree arc that was. So I'm not going to be able to use his inscribedness to answer this question. So I'm going to have to find something else. Okay. Well, something else that I notice is that this angle right here is a central angle, and he's intercepting the 134, which means this central angle is also 134. And now that I know that, I can use my handy dandy triangle sum theorem, and I can use that route to figure out what the measure of angle C is by simply just subtracting 23 and 134 from 180, right, to figure out that's 23 degrees. Or, I know what some of y'all are thinking, you're like, Miss Jester, I don't even have to do all that work. And you're right, because I also can notice that these are both radii of the triangle, which makes that an isosceles triangle, which means my congruent base angles have to be present. So of course the C has to be 23 degrees, right? So many connections happening from everything that we've learned all year long going on there. All right, next up is ABD. Let's see, where's that? ABD. Oh, yay, we already have that labeled. It's 49. We just talked through that earlier. Feel free to rewind if you need to. And then we need the measure of angle A. All right, well, we're kind of in the exact same boat. Now that we've had this conversation, we can do this the short way, right? Because we definitely have another isosceles triangle. Let me kind of right? This right here is an isosceles triangle because he also has the 2 radii for sides. And of course, he's also going to have these congruent base angles. So angle A also has to be 49 degrees. Or you can do what I did before, and we know that this central angle has to be 82 to match his intercepted arc. And then you could figure out what the third angle of the triangle is, and voila, you're going to get 49. All right, I like that question. I think that's my favorite one so far. All right, now we get into some more formula work. Here we go. Find the value of x. It says to the nearest tenth if we need to, and we're going to assume everything that appears tangent is tangent. Okay, so on number 38, we definitely have a secant, and we have a tangent. Now this tangent line goes on forever, but I really don't care about this forever part. I only care about the x length from this point to our point of tangency. So I'm going to kind of scribble out the rest of that. I don't need it. And so we just learned this the other day, right? Again, this is the bottom box on your formula chart where you're looking for segment lengths. So this is going to be outside times whole thing equals outside times whole thing, right? So that's going to give me x times x for the tangent piece because the outside is the whole thing. You can go ahead and write x squared if you want. Equals, for the secant, we've got the outside part of 4, and that's getting multiplied by the whole thing, which is clearly 9 by adding the pieces together. And you can see that that's going to give us x squared equals 36, so x equals 6. Technically plus or minus 6, but we can't use the negative. All right, moving on to this problem. This is clearly 2 secants, so we're using the exact same formula we just did on the previous problem. We're going to do outside times whole thing equals outside times whole thing. Okay, now this one's a little bit trickier because on this one they're giving me the whole thing, but they didn't give me an expression for the outside, but they did tell me the inside is 10, which means we will be responsible for recognizing that the outside then must be x minus 10. Right, so we can write our own expression in for that. So here we go. So the outside is x minus 10, and the whole thing is x. And then on the other secant, the outside is 8, and the whole thing is 12. And obviously, wherever you have a binomial, you're going to have to distribute. So that's going to give us x squared minus 10x, and that's going to give us 96. Clearly, we're ending up with a quadratic, so we need to factor him. So we need to set him equal to 0 first. He's a trinomial, so we're going to just do normal factoring. We need the 2 numbers that multiply to give us 96. But combined to give us negative 10. And what's that going to be? I think that's going to be 16 and 6. And the 16 has to take the negative. It's because that's a negative 10. And then we set each factor equal to 0. And that's going to give us x equals 16, which is looking good, and x equals negative 6, which is not going to work for this particular problem, right? And so that's going to be our go-to answer of 16. All right, number 40. All right, number 40, I'm going to point these out whenever we hit them. I'm going to kind of circle this guy. This is from day 3. This is from last Friday. This is stuff that is not on the formula chart. So the name of the game for day 3 was find the right triangle. And if you can't find a right triangle, then you find yourself an isosceles triangle that you can cut in half and make a right triangle, right? So that's totally the name of the game. If it's not on your formula chart, you need to find a right triangle. So on this picture, I don't see a right triangle, but that's only because for some weird reason, they decided to draw the radius over here. That radius of 10 does me absolutely no good right there. So I'm going to draw that radius of 10 right here because I need him. That's not a very good place to draw that. I need to form this right triangle right here. Sorry, looking for a highlighter. Right, and again, if it's not on your formula chart, if it looks like a picture and you don't see it anywhere on the formula chart, then you need to find a right triangle. Okay, now obviously there's a couple of exceptions to that rule, but it's going to help you out 90% of the time. Now this is a tricky one kind of for people because at first it's kind of hard to notice. We know the hypotenuse of this right triangle is 10 clearly because that's the radius, and we're looking for this leg, but then it's like, well, what do I put here? Again, this is totally not drawn to scale, but don't ever trust scales of drawing anyway. So the thing to catch here is that this is also a radius, and I know that whole thing is 10. So if that little piece over there on the right is 4, then that must mean this has to be 6. Again, I know that doesn't look like to scale, but that's okay. And now we can do Pythagorean theorem and solve our right triangle. X squared plus 6 squared equals 10 squared. All right, so x squared equals 64, so x equals 8. Or, of course, you can just recognize that this is a 3, 4, 5 Pythagorean triple, and you can just jump right to the answer. Okay. All right, number 41. Well, this is more of the same of what we just did on numbers 38 and 39, right? These are two secants. We're looking for segment lengths. So we're doing outside times whole thing equals outside times whole thing. So I'm going to erase that mess I just made. So I'm going to do this top secant first. So the outside is 9 and the whole thing is 21. Then on this secant, the outside is 8 and the whole thing is x plus 8. And voila, right? That's your algebra equation. So let's see, what's that going to give us? 189 equals 8x plus 64. Right, so we're going to subtract our 64 from that 189. We're going to get 125 equals 8x. And then we're going to divide by x. And we're going to get 15.625. Now, I know the directions say to round to the nearest tenth. But there is no need to round to the nearest tenth when it's a finite decimal. So if you wrote 15.6 on the test, I'd be fine with that because that's what the directions said. But again, the only reason I would ever actually need to round to the nearest tenth is if it was an infinite decimal and didn't ever end. And this one does, so I'm just going to leave it exact. Okay? All right. Here we go. 2/3 of the way done. If CE is 6, okay, 6, and CD is 16. Okay, so let's understand what we just said here. So CD is 16. Now, clearly, I don't need the 16. I need the ED length, which is obviously 10. Right? So that's what that's trying to tell me. So I'm going to erase the 16. And then what do we got? AB is 17. Ooh, this one's tricky. So all of this is 17. Now, what makes this problem gross is, I mean, it's not that bad, but what makes it bad, though, is that these are chords that are intersecting. And we know when we look at the formula chart that the formula for intersecting chords is piece times piece equaling this piece times this piece. The products of each chord are equal to each other. Well, the problem is I've got the 6 and the 10, so I'm liking that. Let me write that over here, 6 times 10. But now I need the 2 pieces of this chord. And they didn't give me the 2 pieces of that chord. They just told me the whole thing was 17. So you're going to have to write expressions for those 2 pieces of the chord. So basically, you just need to designate one of them as x. I don't care which one, and it doesn't matter. So if I make that one x, then this one is going to be 17 minus x. And now I have an expression for each chord. So now I can use them in my formula. Piece times piece equals this piece times this piece. All right, and that's what we're going to solve. So 60 equals 17x minus x squared. So clearly this is going to be a quadratic, right? Now when I solve a quadratic, I do not want the x squared to be negative. So I'm going to take these guys over to the left to get this set equal to 0 because I want my x squared to be positive when I try to factor. Right? So now we're looking for the only two numbers in the world that multiply to give us 60, but add to give us negative 17. And that is going to be negative 12 and negative 5. Now this one's a little different, right? Because when I solve both of these factors, I get x equals 12 or x equals 5. Which means, and both of those answers are legit, right? Because you're basically saying either this one can be 5 and this one can be 12, or this one can be 5 and this one can be 12. Now, I know there's clearly a longer and a shorter one, but again, we can't trust the scales of pictures. So both of those answers are totally fine, right? So, and usable. So we want to make sure over here when it says, what is the length of EB? Well, the way I've solved it, EB is I put X there, but I could have just as easily put X here, right? So I am actually going to write that EB could be 5 or 12. And then when it asks me for the length of AE, well, he could be either 12 or 5. Now, I just switched it around because I want the corresponding ones to add up to 17. If you just wrote 5 or 12 again, I don't care. Okay, but there's two solutions. They both work. And if they both work, then you need to write both. Okay, if you just write one of them, then it's going to be wrong. Half wrong. All right, let's go take a peek at this one. AC is 3. Oh, that's a very tiny little segment right there. And BC is 5. So that's this segment length. And AD is 2. Okay. Find each measure. Okay, well, there's two major things you have to notice happening in this picture. The first one is that this is a secant and this is a secant. And we are clearly missing this piece right here. So I'm going to refer to that piece as X, this whole thing. Because remember, the formula is outside times whole thing, and then outside times whole thing. So I need to use X to represent ED so I can actually put something in my formula. Okay, so overall that's a pretty easy one. So outside, I'm going to do this secant first. The outside is 3. The whole thing is 8. So 3 times 8. And then the other secant, the outside is 2. And the whole thing would be x plus 2. And that's a really quick algebra equation, right? So we're going to distribute our 2, 2x plus 4, subtract the 4, divide by 2, and we get 10, right? So this is 10. But then we don't want to let it pass us by, recognizing that ED is not just 10, but he's also a diameter, right? And again, you have to catch those diameters when they're drawn in pictures, right? Because they're really going to help you out. So if that diameter is 10, that means every single radius I see in this picture is 5. So 5, 5, 5. All of those radii are 5. Now, I know this says 5, and that doesn't look like it's 5, but again, just roll with it because it's just not drawn to scale. Okay? All right, so let's go see if we've answered any of these questions. The length of PD. Oh, look, that's one of our diameter, or radii, sorry. So 5. ED, well, that's what we solved for, right? That was the whole diameter of 10. So 10. And then PB. Oh, well, PD, another radius. So 5. Again, not a lot of math. Look, we just did this tiny little algebra equation, but you have to recognize what equation to use and then how does that affect everything else in my picture. Okay? All right, deep breaths. Number 47, getting close. All right, everything in this section right here is all from day 3. And remember, the name of the game is to find yourself a right triangle, right? Most of the time. There are some exceptions to this, which would be numbers 47 and 49. So on number 49, all they're showing you is that you have 2 tangent segments, both coming from the same external point. Again, you can ignore that these are going to infinity. I don't care about those. I only care about the 40 and the 3x plus 4 being the segment lengths. And we learned the rule that if 2 tangents are extending from the same external point, then they must be congruent. So all you have to do is set those equal to each other. So 40 equals 3x plus 4. So just subtract your 4, and you're going to get 12. And again, these are so easy to check just by plugging them back in if you want to. All right, number 48. So on number 48, you have to remember the rule that a radius is always perpendicular to a tangent at the point of tangency. And so again, remember I told you the name of the game is find yourself a right triangle, and here's our right triangle. And then so we're going to do Pythagorean theorem. This is a Pythagorean theorem problem. And then I need to recognize that if this radius is x, then this radius is x. So I'm going to label that accordingly, which then tells me that this entire hypotenuse is the expression x plus 8. And now I can do Pythagorean theorem. So x squared plus 12 squared equals x plus 8 squared. All right, so here we go. X squared plus 144. Please, 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 when you square a binomial, please do not try to distribute the square and just square the x and the 8. You are not allowed to do that because the plus sign making it a binomial. You must remember, and we even talked about this on the last day, that squared binomials can be written twice, and then you have to FOIL that out. So this is going to give us x squared plus 16x plus 64. I went ahead and added the 8x plus 8x in the middle if everyone's okay with that. And then I'm going to bring down the left side. And then there's our algebra equation. Got rid of all those parentheses. Clearly the x squareds are going to cancel each other out because they'll subtract away. Right? And so we are just going to subtract the 64 over, which is going to give us 80. And 16x over here. And when we divide, we're going to get 5. So x equals 5. And again, you can check your answers. I can plug this in, and it's a 5 here and a 13 here. Oh my gosh, 5, 12, 13, Pythagorean triple. Of course, x is 5. Right, so easy to check those answers and make sure they work. All right, number 49. This one is using the same little factoid from number 47, that tangents that extend from the same external point are congruent. So I know that if this is 3, that this length must also be 3, right here. And if this length is 4, then this length must also be 4. So literally all you have to do to solve for x is just add the 3 and the 4 together. So clearly x equals 7. It's just a matter of knowing the rule about tangents. All right, over here, number 50. Yikes, this looks like a complex problem. Okay. Trying to think. Okay. So a couple of things are happening here. Number one, I know that I might be saying a lot of unnecessary information, but just roll with it here. I know that this is a tangent and this is a tangent, which means that they are congruent because they're stemming both from external point C, which means that this is an isosceles triangle, right? So that means that our base angles must be congruent, which proves that this angle right here must be a 60-degree angle, right? And the whole triangle itself then proves that it's not just isosceles, it's also equilateral. So this whole angle up here, oopsies, must also be 60 degrees. Okay. Well, if that's an isosceles triangle, then then this must be a height dropping, and I can prove that because if I draw in another radius right here, then this whole figure is actually a kite. And we know the diagonals of a kite are perpendicular. I know that's kind of a stretch, but just using all those things that we've learned. And of course, that means that this is a 30 degree angle. I'm splitting the 60 in half. And I'm just going to keep going. We also know that anytime you have a piece of a diameter that is perpendicular to a chord, that automatically means that the chord is being bisected, which means this side is also 6, which of course makes sense because this whole thing is just one giant symmetric kite, right? So of course the top half is the exact same as the bottom half. All right. We still haven't solved for x yet, and that's okay. So x, I'm going to focus my attention now on this right triangle, right? Which obviously is a right triangle because that's a right angle. So that's a right angle, right? Now, the other thing I know about what happens when a radius meets up with a tangent is I know that this is a right angle, which then proves that this is a 30-degree angle, which then proves that this is the 60-degree angle. So this little orange triangle that I've highlighted is a 30, 60, 90. Okay, hopefully that is making total sense. Right? And so we're solving, let me just kind of draw over here what we've got now. My picture is just a total mess. So now that little orange highlighted, I have a 30-degree angle, a 60-degree angle. I know this is 6, and I'm looking for the hypotenuse. Make sure I have all that correct. There we go. Well, the 6 is the long leg. So I know that in a 30, 60, 90, the long leg is short square root 3, right? So long 6 equals short root 3. Remember, this is the short leg, not x. X is the hypotenuse, but I've got to find the short leg before I can find the hypotenuse. So that means that 6 over root 3 is the short leg because I got to divide by 3 on both sides. Then I have to rationalize my denominator, which is going to give me 6 root 3 over 3, which is going to give me 2 root 3. Oh my goodness. And that's the short leg. So this is 2 root 3. And then, of course, the hypotenuse, I'll just go ahead and write the rule, The hypotenuse is double the short leg in a 30, 60, 90. So we're going to multiply 2 times 2 root 3, which is 4 root 3. Wow. That is a lot of thinking. Now, did I have to go through every single minute step of that? No, right? But I want you to kind of see how that picture is going. It kind of breaks down and how I can prove, but all those triangles, that all of those are 30, 60, 90s. Whew, all right, feel free to rewind and listen to that one more time if you need to. All right, moving along. Number 51, we've already seen a question exactly like this before. We've got a radius hitting a tangent. So therefore, this is a right triangle. And if I have a right triangle, then I'm going to be solving the right triangle. So we're going to be doing some Pythagorean theorem. Now on this one, we're actually solving for one of the legs because we know that this is a radius of 4, which means our entire hypotenuse is clearly 12. So when we set up our Pythagorean theorem, right, we're doing x squared plus 4 squared equals 12 squared. All right, so we've got our 12 squared. We're going to subtract the 4 squared, which is going to give us 128. And then we're going to, that's not a perfect square, but it does break down into 2 times 64. And 64 is a perfect square. So 8 root 2 is going to be our solution there. Again, exact answers only unless it tells us to round to the nearest tenth. All right, this one was actually on your quiz. This exact question was on your quiz, basically. This number might have been different, but the 120 was the same. When it says find AB, please understand that means to find the length of AB. It's not asking for the arc AB, or else it would have said that, right? It says find the length of AB. Well, I don't see any triangles, so you need to make a triangle, right? And the one thing I definitely know about this triangle is actually 2 things. It's isosceles, because those are both radii, and because this arc is 120 degrees, that means this central angle is 120 degrees. So essentially, at the end of the day, again, I kind of like to draw my triangles over here a little bit. There we go. So I've got an isosceles triangle where this is 6 and 6, and this is 120, and basically I'm finding x, right? AB is the length of the base, that highlighted piece. Let me kind of highlight that so we can see the connection there. There we go. All right, and so I can only solve right triangles, so this one's not doing me any good. So as we know, we're going to drop, ooh, not like that. There we go. Oh my gosh, my battery's almost dead. I'm going to have to go really fast. Here we go. So that's going to make a 60, a 30, 60, 90. Which means that my short leg is 3, which means this is 3 root 3. And if that side is 3 root 3, then this side is 3 root 3, which means AB, or x, is 6 root 3. Voila. Oh my gosh, I'm going to have to go really fast, guys. Here we go. All right, find the measure to the nearest tenth. Okay, they want us to find the measure of arc BC. Well, we have all these congruent chords, and we learned a property on day 3 that says if we have congruent chords, that means we have congruent arcs, right? So all I have to do at the end of the day is take my 360 degrees full circle and divide it into 5 congruent arcs. So the measure of arc BC is going to be 72 degrees. All right, number 54. This action right here, sorry, those boxes are really sloppy, right? All this right here is telling us that these 2 chords are equidistant from the center. And if 2 chords are equidistant from the center, that means that they are congruent, right? I also know, this is kind of a 2 for 1. I also know if a piece of a diameter is perpendicular to a chord, it bisects that chord, right? And so, erase all this business. So that means this half is also 12, which means this whole chord is 24. And since this chord is equidistant from the center, he's also going to be 24. So x equals 12, y equals 24. I don't know why that y is capitalized. That looks really weird. Okay. All right. Oh my goodness. If I don't make it and the video shuts off, well, oh my gosh, I'm never going to make it with 10%. Let me see if I can find a plug. Hold on, really quick. Okay, I've returned. With maybe. Oh my gosh, okay. I don't even know if that's going to make it. All right, here we go. Suppose a chord of a circle is 16 inches long. Okay, I'm just going to draw a circle. I'm going to draw a chord, 16. It's 6 inches from the center, okay? So remember, distance is always measured perpendicularly. Find the length of the radius. Okay, we just talked about this. When you've got a piece of a diameter perpendicular to a chord, that means he's bisecting. So we know that each piece of this is 8. And then I need the radius, so I'm going to draw that in because remember, we're looking for right triangles. And so I'm just going to solve that right triangle, right? So again, it's just Pythagorean theorem, 6 squared plus 8 squared equals radius squared. And that's going to give us 100 equals r squared. So r is 10, which makes sense because it's a 3, 4, 5. Oh, and you know, let me put inches since it gave us units. All right. Number 56, find the length of the chord. This is going to be basically the same type of question, but we're solving for something different. Find the length of the chord that is 5 inches from the center. Okay, so again, that has to be perpendicular because distance is always perpendicular with a radius of 13. Now I'm really hoping, obviously these are congruent because the diameter is perpendicular to the chord, which splits it in half. And that's going to be 12 because that's a 5, 12, 13 Pythagorean triple. If you don't know that triple by now, you can just do a quick little Pythagorean theorem. So if that side is 12, that side is 12. So that means the length of the chord is 24 inches. Okay. All right, number 57. Suppose the radius of a circle is 17 units. Again, it's the same exact question. We're being given different information. So here's the radius, 17 inches or units. The chord is 30. All right, so here's 30. What is the distance from the center of the circle to the chord? Oops, that's not very good. Oh my gosh. Gonna bug me. There we go. So it's looking for this. So once again, I have a diameter hitting a chord, which means it's splitting it in half. And that means this piece is 15. So I'm just doing a quick Pythagorean theorem or using my Pythagorean triples. All right, this is going to give me x squared equals 64, so x equals 8, because that's an 8, 15, 17 Pythagorean triple. Okay, so it's the exact same question and picture. You're just being given different things and being asked to find different things. All right, number 58. This one we've talked about numerous times. This is a trapezoid, but we can't really solve it as a trapezoid, so we need to split it up into a rectangle on top of a right triangle. And so here's our right triangle. We know that this leg is 24. The x is the hypotenuse. That's kind of in a weird spot now that I've covered it up. And then we now know that if this is 5, this is 5, which means this piece is 4. There we have it. So now we've got a little Pythagorean theorem. 4 squared plus 24 squared equals x squared. Oh, hold on one second. All right. Sorry, my cord is restricting my movement to where I was working. Okay, so you can do that Pythagorean theorem yourself, I'm sure, right? And it's not a very friendly number, right? It's going to break down to 4 root 37 if you were to do the math. Okay. All right, number 59. Oh my goodness, how do I make it? So number 59, this was actually in our notes, this exact same question, right? So the 3 feet right here is referring to this piece right there. And we know that all tangents are congruent from the same external point, which means this piece is also 3, which means this piece right here is 5, which means this piece is 5, which means this piece is 4, which means this piece is 4, and then this 12, which is technically a diameter of my circle, so you can think of it as being 6 and 6, which means these pieces are 6 and 6. Right, so we're just using that congruent tangent rule, and then you just have to add up all the pieces, right? And this gives us a perimeter of 48 feet. Again, this exact same question was in our notes. Okay. So you can go back and look at that if you want to. All right, number 60. All right, again, I'm hoping we've seen these so many times at this point. I'm hoping you're like, okay, I finally get it. Right? So the name of the game on pictures that look like this is to find a right triangle. So the radius here does me absolutely no good, right? So I'm going to redraw my radius here, create myself a little right triangle here so that I can solve for this missing side right here. Okay, I'm going to call that A. So A squared plus 2 squared equals 3 squared. So that's going to give me A squared equals 5. So A equals the square root of 5. But I'm not done, right? Because they wanted this whole chord length. But because this is a diameter perpendicular to that chord, I know it's splitting the chord in half into 2 congruent pieces. So I'm going to multiply this by 2. So x is going to be 2 root 5. Okay. All right, number 61. Looks like I have a quadrilateral trapped inside of a circle or inscribed in a circle. So remember what that means is that the opposite angles are supplementary whenever that is happening. That was our rule from day 1. So that means this is 130 degrees because these 2 angles are supplementary. And we know that this guy is 89 degrees because these 2 angles are supplementary, right? So I'm sure that's our first 2 questions, right? The measure of angle B is 89 degrees. The measure of angle C is 130 degrees. Then it wants us to find all these arcs over here. Well, that's going to be pretty darn easy because every single one of these angles is an inscribed angle, right? So all you have to do is go use the inscribed angles to find the arcs. So the first one is arc BD. Okay, well here's arc BD, and he is being intercepted by inscribed angle A of 50 degrees. And inscribed angles are half their arcs, so that means the arc has to be 100 degrees. All right, again, erase, start over. Okay. What are we doing now? ABC. A, B, C. Well, that arc is clearly being intercepted by angle D, that 91 degree angle. So he's going to be 182 degrees. Right. Then DAB, oops, D to A to B, he's being intercepted by the 130-degree angle. So that arc's going to be 260. Okay, voila. Oh my gosh. Okay, this one, I don't really have time. Maybe we can go over this in class. If I have time, if my iPad doesn't die, I'll come back and do this question. Let's go look at these really quick. So number 62, these last few questions, find the length of CD. All right, it wants the length. All right, well, clearly this is a 112-degree angle right here, and that's the central angle. So that means that this arc is taking up 112 3/60ths of the circumference of this circle. Let's see, and they did tell me that EB, which is the radius, is 15, which I totally need, right? So the length of CD is going to be the fraction of the circumference. So I want 112 3/60ths of the 3 pi, right? And sorry, I can't even reach my calculator. Making a mess. So that's going to give us 28 pi over 3. And of course, that's going to be centimeters, right? All right, on this guy, find the length of arc TS. Okay, well, TS is here. It looks like I have 2 diameters going on here, right? We've got this diameter and this diameter, which is creating like this vertical angles situation where I know this whole angle right here has to add up to 128, but I already know this angle is 31, right? So I can totally subtract that away and figure out that this is 97 degrees. So I kind of have to figure all that out first, right? Okay, I'm gonna erase all that mess that I just made. All right, and so if that's 97 degrees, then the arc is 97 degrees. I don't really have to know that part. So that means that this arc that we're looking for is taking up 90 3/60ths of the total circumference, which is going to be 2 pi 4.5. And they tell us the radius is 4.5 up there in the verbiage, right? And so that's going to give us 97 pi over 40. And that would be millimeters. We don't see millimeters very often. Sorry, units, but there you go. If you want to, you can write that as 2.425 pi, since that is a finite decimal, so that would be okay too. All right, oh my gosh, the home stretch. Here we go. Find the area of the shaded sector. So this is going to be fraction of the area, right? So if the radius is 20, we can clearly see that this sector is taking up 119 3/60ths of the total pi r squared area. So clearly the area of the circle is 400 pi, but we only want 119 3/60ths of it. None of that's friendly numbers, so that's going to give me this lovely answer of 1190 pi over 9. Oops, 9 square feet. Okay. All right, the shaded region here, clearly this is taking up 3/4 or 270 3/60ths of the circle. You're more than welcome to just write 3/4 of pi, oh my gosh, why are they so awful? 29.5 squared. And again, just chunk all of that in your calculator. Take not the pi though, you're gonna just keep the pi in your answer. Oh my gosh, and that lovely number, if we type that into our calculator, 10,443 pi over 16 square miles. Who came up with these numbers? Those are crazy. Right. It is a finite decimal too, right? It's 652.6875. So if you want to write that, you're more than welcome to. All right. Last thing really quick is that these are talking about the radians. And so remember, anytime you're talking about arc length and radians, you want to use that easy peasy top right formula on your formula chart that says L equals R theta. That's the formula we're going to be using. And you're only allowed to use this if it's in radians. If it's not in radians, then you have to use the fraction of the circumference that we did on numbers 62 and 63, right? But here we go. They're obviously asking us to find the theta or the central angle. So, and they gave us the arc length and the radius. So literally all you have to do is say, oh, the arc length was 6 pi, the radius is 12, put your theta in there, or x. If you want to change it to x, you're more than welcome to. So all you have to do is divide by 12 on both sides to get the theta solved for, and then just reduce. That's going to be pi over 2. Ta-da! And that's pi over 2 radians. Here, I'll write that down. I'm not going to make you write the word radians. If you see a theta and a pi, we automatically know it's radians. That's automatically assumed, but you can definitely write it. And the rest of these are exactly the same. They're just asking you to solve for maybe something a little bit different. This one's actually not. This one's still asking you to solve for theta. So we're going to use the L, which is 11, equals radius times theta. So clearly all I'm doing is dividing by 8 to solve for the theta. So theta is 11/8 radians. Or 11, yeah, that would be plural, so more than one. Notice it doesn't have a pi in it, but remember the little demonstration I did on the board, right? Radians don't have to have pi. They just typically do. Right? All right, and then this guy over here, same exact question. The arc length is 5 pi over 2. And then we're going to multiply that time or equal that to 3 theta. L equals R theta. And all you have to do is divide by 3 on both sides. There we go. And if you divide 5/2 by 3, right, you're going to end up, well, here, I'll show you off to the side really quick just so I don't confuse anybody. You can obviously do this in your calculator and it'll give you the answer. Theta. There we go. Remember, 5/2 divided by 3. Remember, dividing by 3 over 1 is the same thing as multiplying by 1/3, right? So that's going to give us 5/6. So 5 pi over 6 radians. Again, you can just type it in your calculator if you want to. 5/2 divided by 3, and it's going to tell you that it's 5/6. Right? Oh my gosh, I have no idea. What time is it? Oh my goodness. It's a long video, I'm sorry. All right, just for giggles, why not? Let's go tackle this big circle question here. All right. Let's see if we can do this really quick. If my iPad dies, I'm sorry. All right, so the measure of arc AB is 60. The measure of arc BC is 30. And ED, where's that? 20. All right, and I definitely do not want to lose the fact that clearly EB is a diameter in this picture, which is going to help me immensely because if EB is a diameter, I automatically know this half has to add up to 180, which tells me that this is 120, and I know the bottom half has to add up to 180, and 50 degrees is already taken up, so this has to be 130. So just getting all of my outer arcs taken care of is going to be super helpful here. Another thing I happen to notice is angle 1. Angle 1 is a central angle. Oops. I'm going to kind of emphasize the center P here. Angle 1 is a central angle, which means he is the same measure as his intercepted arc. So there's your 30 degrees. I'm not sure if I can go in order here, but I'm going to try. Angle 2 is right here, and he's an inscribed angle, which means he's going to be half of his intercepted arc. So he's also going to be 30 degrees. Okay, I'm going to erase my mess as I make it and kind of go back. All right, angle 3. Actually, let me write that in just in case I need him later. There we go. Angle 3 is also an inscribed angle, so he's half of his intercepted arc. So he's going to be 10 degrees. Okay, I'm going to write that in. There we go. Angle 4. Where are you, angle 4? Oh, angle 4. He is an inside angle being created by two chords. So him and his little vertical angle buddy across the way, we know their measure is the average or half the sum of their two intercepted arcs, which we happen to know. So I'm just going to write that down here. So the measure of angle 4 is half of 60 plus 20. And that's half of 80, which is 40. So angle 4 is 40 degrees. All right, take all that away. I'm going to go ahead and put 40 degrees here and here in case I need that again. All right, if you want to, you can go ahead and put the 140. I know they're not numbered, but maybe it'll help us. You never know, right? They're little linear pair buddies right next door. Okay. Let's see, the measure of angle 5. Where are you, angle 5? There you are. So angle 5, let me get it. I'll use red. Angle 5 is this angle whose vertex is on the circle. So he's also half of his intercepted arc of 120. So that means he's 60 degrees. All right. So let me write that in, 60 degrees. Where are we at? Angle 6. Angle 6, here we go. This is angle 6. He's an inscribed angle. So he's half of his intercepted arc. And his intercepted arc is the 60 plus 30, so he's half of 90. So he's 45. Okay. Then we got angle 7. Oh, let me write that in. 45, just in case. There we go. Angle 7 is this outside angle here in the bottom left corner. And we know outside angles are half the difference of their intercepted arc. So here we go. The measure of angle 7 is half of 90 minus 20. So half of 70, 35 degrees. Equals 35 degrees. All right, oh my gosh, we're so close. The measure of angle 8. Oh yeah, we can find him, right? He's an inscribed angle. He's intercepting all of that, which is 160 degrees, which means half of that. So he's 80. About here, 80. There we go. Okay, finishing up here, angle 9. Where are you? There you are. Angle 9 is this angle, also inscribed. So he's going to be half of his intercepted arc. So half of the 120, so he's going to be 60. All right, let me write that in, 60, just to be careful. And notice a couple of things I can kind of be checking along the way. Notice we have a little triangle here, and notice that all three of those angles add up to 180, so I'm feeling pretty good. Then angle 10 is our very last one. Angle 10 is being formed by the tangent and the chord. But his vertex is on the circle, which means he is half of his intercepted arc. So he's going to be 30 degrees. I also know he's 30 degrees because all four all four of these angles, 5, 3, 8, and 10, they all have to add up to 180 because they're all forming that tangent line, right? And so I know that that has to be 30 because that's all the degrees left to reach 180. So that's another way you could find that angle. Oh my goodness, you guys, there we have it. Every single question on this review. I know that was a lot, right? So I'm going to scroll back through all this wonderfulness. Right? And of course, I'm hoping you understand all that after the explanations and all that good stuff. All right. Study. Good luck on your test tomorrow. Talk to you later.